Let's evaluate how reaction rates vary over time. We in fact will see that most reactions, by and large, do not follow a linear reaction rate. We're going to see that because reaction rates depend on concentration, since they depend on concentration, and as we know that concentration decreases over time of a reactant, that the rate will also slow down. So we see that reaction rates tend to slow over the course of a reaction. And in our last video, we kind of looked at the entire reaction. We saw, okay, well, we had the start and the finish, and then we saw how long that took, and that was our average rate. But what's more interesting, perhaps, is the instantaneous rate of a reaction, where we're looking at a small time interval. In our past example, it took 30 seconds for the reaction to complete. But what if we took a sample at 5 seconds? What might we see about the rate during those first 5 seconds? What about the time period between 10 seconds and 15 seconds? What would the rates look like then? So we would expect, actually, that the rate for the very first 5 seconds should be faster than the rate at the very end 5 seconds, because concentration and rate are interdependent. And so if we take a look at some data, which I have miraculously copied here, ta-da! Here's some data points. If we look at time of sampling and the concentration that we've measured at that time, we can get some data, or we can get some points, right? So every 50 seconds I've taken a measurement, and we've got the results of that measurement under the concentration here. And if we take the rate of each of those time intervals, we see the important part here is that that rate is slowing down. And that's to be expected. Most reactions follow this pattern, where their rate slows down over time. Only one set of reactions, one group, has a fixed rate. And that's typically, again, not very common. So we see that the rate is slowing over time. And that's, again, pretty common. Graphically speaking, this set of data may look like the following. We don't see a linear decrease over time, but we see a rather exponential one. If we say this is this is time here, and we have our concentration of reactant A. This is what a graph might look like. We see that at the beginning of the reaction, in a very short amount of time, we may use up a good deal of concentration. And let's say that this is, a 10-second time interval here, and we will have used a good amount of reactant. Let's say we take another 10-second time interval. We can see that, at this point in our graph, we've used a lot less of that concentration in the same amount of time. In other words, we see that the slope is decreasing in magnitude. The slope is going to be negative here, of course, because we have a decrease in concentration, but the magnitude of the slope is decreasing. Remember that for the slope, that's always going to be our rise over run, right? So it's going to be our difference in y minus our difference in x. So this case is concentration over time, right? Because our y-axis is concentration, our x-axis is time. Remember, that's the same thing as change in concentration of A over the change in time. And so again, we're going to see that the slope will be negative, so that's why we put the negative in there later to get rid of that, to cancel it out. But we see that here we have the slope of the tangent line to these curves at these points. We don't have to do the calculus here, but really it's dA dt. We could say that as well. Although, again, we will not need calculus to solve anything here. d is the same as delta, right? It's just in calculus we look at very, very tiny time intervals, almost instantaneous. And again, we're looking at the, kind of the smaller intervals of time we're looking at, the better information we're going to have. That's again where calculus is more useful for this, but we don't need that for Gen Chem. We're really just looking at patterns here. We see that the slope tends to decrease in magnitude over time because our reactants are being consumed, and they're being consumed exponentially. So very quickly at the beginning, slower towards the end of the reaction. And so, oftentimes, just kind of to kind of standardize this, so that when we're comparing things, we really only look at the instantaneous rate at the very beginning of the reaction. We call this the initial rate. We look at the initial rate of reaction, and that initial rate is essentially the instantaneous rate at time 0. So right at the start of the reaction, how quickly does that reaction proceed? And we're going to see that, again, this is not something we're going to necessarily calculate. These are going to be data points given to us. So instantaneous rate is that rate at one tiny interval. We're looking at, again, an infinitesimally small time window, so we can get the rate right at the start. Once we do that, we can see, okay, if reactions are going to obey similar laws, we'll see that if one reaction proceeds faster at time 0 than another, we can get information about that. We have more information about how quickly that reaction is going to proceed versus others. We can do some formulas and fun stuff. So with that, looking at initial rates is going to be something that we're going to use to compare in order to determine what are called rate laws. And that's going to be covered in the next video.